So today we're going to learn the 12-2 lesson. And in order to understand the 12-2 lesson, first we need to jump back to 3-2 and refresh on a couple of things from regression. So the first thing I want to look at is just what a scatter plot is. And a scatter plot is the relationship between two quantitative variables. And so the one that we're going to look at here is the data from the 2019-2020 English Premier League season. So it's the team, the number of goals they scored or goals for, and then it's the total number of points that the team received in the whole season. So remember, in soccer leagues, teams get points for winning games. They get 3 points for winning a game. They get 1 point for a tie, and they get 0 points for loss. And the team at the end of the season with the most points wins the league. So there is the scatter plot. Now, usually a scatter plot, we don't have the line, we don't have these red lines here, but I want to talk about those here in a second. So to describe a scatter plot, we should describe shape, direction, form, and strength. So this relationship here, the form looks linear because it follows a linear model. The direction is positive because as the goals for increases, the points increase. And the strength is, I would say, strong or moderately strong for this relationship. Now, remember, our measurement of strength is called the correlation. And the strongest correlation is 1 or -1, and the weakest correlation is 0. So this right here equation is called our linear model, or the least squares regression line. And this would be our slope. This is our x variable or explanatory. And points is this is predicted points because it has a y hat on top. So, or a hat on top. So there's a difference between, like, if you look at Liverpool had 99 points and they had 85 goals for. So if you follow to 85 goals, you can follow up, and there is Liverpool's dot where they scored 99 points. But our prediction, if we use this model, is not perfectly accurate. Our prediction is going to give you a point on the line here. So if we plug in 85, we're going to get this point right here, which is about 80. So that's what we did here. I plugged it in, plugged in 85 for X, and we got a predicted of 80.242 points. So there's a difference, and that difference between the actual number of points the team had and the predicted is called the residual. So Liverpool's residual would be their actual minus the predicted. So there's a residual of positive 18.76. So what that means here is this line underestimated how many points Liverpool scored or earned based on their number of goals for. So just a quick reminder of what scatter plot is, what a residual is, and a linear model. The next thing we need to know is the purpose of a residual plot. So here's a residual plot, and the residual is, it's the normal x-axis, so it shows the number of goals for here, and then it shows the residual for every point. So this red line right here is the distance. It would be the residual, and you'd plot that. So if you look here, here's Liverpool's residual, positive 18.24. And we did it for every other point as well. So the purpose of this residual plot is to answer the question, is this linear model appropriate? And what we want the residual plot to show is even scatter above and below and no obvious pattern. So we don't want to see any curves in the residual plot. We don't want to see it getting smaller and then larger as we go across. We want it to be evenly scattered. And so you can see here that this residual plot is pretty evenly scattered. There's no obvious pattern in the plot. So this linear model that we used is a good fit for this data. The other thing you can do to see if the linear model is appropriate is just look at the line. And if it looks like it fits the data well, it looks like there's not a curve in the scatter plot as well, then you should be okay. So you should always check both. So just a quick reminder, the residual plot answers the question, is the linear model a good fit? Now I'm going to scroll down and find the computer output part. Here's the data we're going to use for this computer output part. And it's showing the Ford F-150s, the number of miles they've been driven, and the price that they cost. So as the truck has been driven further, the price decreases because the truck is losing value. So you can see the negative, moderately strong relationship. And the residual plot shows even scatter and no obvious pattern. So this linear model, whatever the equation is a good fit for this line. So we're going to use this data, and I'm going to scroll down to a computer output part. And here we go. Okay. So here is the Minitab output for that data that we were just looking at. And the reason I have this is because you need to be reminded on how to write a linear model or the least squares regression equation when you're seeing this output. So it's pretty simple. You have the constant, which is the y-intercept. So this 38,257 is the y-intercept. And then the coefficient of the x variable, which was miles driven, is your slope. So think about just your equation, y equals mx plus b. M is the slope, which is the coefficient of x. So the coefficient of x is always going to be your slope for your equation. S, just a quick reminder, is the standard deviation of the residuals. That's your typical error of the line, because think about a residual. It's the difference between your point, the actual point, and your predicted point. R squared is the correlation squared. Remember, R squared is it's the variation in Y, so price, explained by the variation in X, which would be the miles driven in this case. We are never going to use the R squared adjusted value, so you don't need to worry about this. I just see people mix them up all the time, so I want to make sure you're aware of that. Now, these are the only things really that you're going to need for this section, but just so you're aware, this T right here is the test statistic. It's the T value or test statistic for this regression output. And this P right here is the P value based on the test statistic. So the P value you can see is essentially 0. And lastly, you do know what this is too. The standard error would be 0.03096. So just so you're aware, these are the values that you really need to know for this. But you should also know what these values are as well.